What's up everyone? This is a video on the trapezoidal rule. So I'm assuming if you've come to this, maybe you've already seen the trapezoidal rule. It looks like this crazy looking formula. I find that it's actually best to really understand the construction of this rule, and then you don't have to remember the formula. So that's what I'm going to walk through in this video, and then we'll also do another example just to make sure you've got it. So first things first, it would probably be good for you to know just the area of a trapezoid. So if you Google this, you will see a very similar image, but I have kind of slightly modified the way that we're looking at the formula. So I've kind of like turned the trapezoid 90 degrees, I guess, to modify this for what we need for today's lesson. So this is the way that I want to think about this. So basically, you might have two different kind of sides here. So you're going to take the average of these two sides and then multiply that by the width. So just keep that in mind, and now we'll get going with this. So here's kind of the idea behind this. Let's say that I've got this function. So just FYI, this will be the function x squared. And let's just do an age-old favorite. So I have it on the closed interval from 0 to 2. Let's say I want to do an area estimate for 4 sub-intervals. So I'm assuming by this point you have probably seen Riemann sums. And so usually when this type of question comes up, then we use rectangles to do our area estimate. So I'm going to go ahead and just first create my 4 sub-intervals. So let's see, here's 1, 2, 3, 4. And now I'm going to show you what makes the trapezoidal rule what it is. So rather than making rectangles, I'm going to make trapezoids, right? So how do I actually construct that? So you come up with your subintervals the same way that you would if you were kind of doing an area estimate, similar to say like a Riemann sum where you've got all equal sized subintervals. And then basically you take the endpoints of each interval, so like this, and then you just connect them like this. So coming from here to here, so again, you've got to take it the two endpoints that are actually on your graph, and then once again, so you connect them. So the short story is then from here, you're basically just going to find the area of each one of these guys. So that part's nice. And you can see by looking at this that this is actually like a way better estimate than using rectangles. So that might have been something you even thought about the first time you did a Riemann sum. Why use rectangles? Why not use a different shape? So the reality is you totally can use other shapes, and there are other rules kind of talking about that. But Riemann sums are kind of based off of the idea the rectangle is very easy to work with and calculate with, right? Because it's just length times width. We can see already with the trapezoid, right? So you've got a lot more things to kind of consider. You've got these two sides and the width. It's just a little bit more to consider. So it's just a slightly more cumbersome formula. But the benefit is at just 4 subintervals, I can just see visually this is probably a much better estimate than working with, say, rectangles. Okay, so now let's get into this. I actually want to kind of explain how the formula is derived by kind of using this example. So I want to view all of these endpoints. Let's label them. So this is x sub 0. We'll call this x1, x2, x3, x4. And of course, the real point, this is 0. This is 0.5. This is 1. This is 1.5, and this is 2. Okay, so I know to actually figure out the area of each one of these trapezoids, I actually need to plug in each one of these endpoints into my function so that I can actually figure out the heights. So let me go ahead then and create just a little table over here. And I'll go ahead and I'll fill in kind of all of these values and evaluate this for y. Okay, so in the interest of time, I just went ahead and filled that in for us, and now we can really get this party started. So let's start with this first little trapezoid here. So I know that I need to take the height of each side. So the heights here are 0, and this endpoint here, this height will be 0.25. So this is 0.25. Divide that by 2. Now I have to determine what's the width. So that's something I haven't actually figured out yet, but the way that you determine the width, this is really the same as what you would do even with a Riemann sum. So you take the last part of the closed interval minus the first part and then divide by the number of subintervals. So this might look very familiar. That's what we always called our delta x. So very similar calculation to working with Riemann sums, really the same. And so basically now I'm going to take this and then multiply this times the width. Okay, so that's the first one. Okay, so now let's move on. Let's keep going here. So what about this one? So how would I figure out the area here? Well, now what I'm going to do is I'm going to take, so the first height was 0.25. So the next height over, that would be this 1 squared, so that's 1. Divide this by 2. Again, multiply that by 0.5. Continuing on, let's go to this one here. So now, let's see, I'm kind of running out of room here, but I think I can do this. So this will be 1 plus 2.25 divided by 2, again, times the same width because it's the same all the way across. And then for this last one, so to get the area of this guy, so this will be 2.25 plus 4 divided by 2, again, times 0.5. Okay, so here's kind of what we got. We're going to take a deeper look at this in a moment, but this is kind of the gist of what you're doing. So hopefully this makes sense, right? This is just the area of each one of these little trapezoids here. Now, one thing I want to point out, so this width in the language of the trapezoidal rule, this is what's known as the step or mesh size. So that's what we call this part here. Okay, so now that I have this whole formula kind of written out, I want to take a look at this one more time. So I'm actually going to restate it. So here it is, and I just want to notice what things every single term kind of has in common because I'd like to factor that out. So the width is the same, right? And then also you're always dividing by 2. So I could actually really factor out this 2 and this over 2 and then this 0.5. All of that could really be factored out. So this will be 0.5 divided by 2. And now I've just got what's kind of left of these calculations, right? So it'll be this and then this and then 1 and 2.25, and I'm still kind of running out of room here, but you can see what we're left with, right? Okay, now that I've written all of this out, well, now you can see actually that I could also make this easier, right? So really, I could multiply this by 2, I could multiply this by 2, I could multiply this by 2. So it's kind of like when you look at the picture, so the endpoints only get added up once, but all of the middle points you're multiplying by 2, right? So if I rewrite this one more time, so this is 0.5 divided by 2, 0 plus 2 times 0.25 plus 2 times 1 plus 2 times 2.25 plus 4. So there's kind of like the shortest way I could write this whole expression, right? Okay, so let me clear a little room because now I want to make an observation. So I had labeled these x points as x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. So let's say then when I actually plug this into the function that these are the corresponding y points. So let's see. If I come over here just to label these, so I'm going to call this one y sub 0, this one will be y sub 1, y sub 2, y sub 3, and y sub 4. And this literally just corresponds with kind of plugging it into the function and what y value you get out. So I want to now kind of convert all of this to a more theoretical language, kind of using that. So for this one, I said this was y sub 0, this one we said was y sub 1, y sub 2, y sub 3, and y sub 4. And then this, what did this correspond to? So I'll just go back and remind you. So this went with the mesh size or step size, this delta x. So this is actually my delta x. And so I could rewrite this formula in very general terms then as delta x divided by 2 y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus y sub 4. And now perhaps this looks very similar. So now I'll show you what the actual trapezoidal rule is. So here's the formal trapezoidal rule. So remember, this is a way of approximating an integral. And so you can do this for n subintervals by using this formula. And this formula now, if this looked really confusing before, you kind of understand now where it's coming from, right? From the construction that we just did. So once you kind of understand, I think, the construction of it, you don't necessarily have to remember the formula. Although, you know, if you kind of get the pattern of it, it can kind of cut down how much you actually have to calculate. So some people, I notice sometimes when I have students doing this, sometimes they will actually just go ahead and revert back to the area of a trapezoid. And if that's how you've got to remember it, I mean, that's fine. But if you feel comfortable with this, right? So to me, it's like, okay, so I have the two endpoints of my closed interval, and then just every other subinterval, I just take 2 times that y value. And I multiply that by this little factor over here. So I like this because I think this is like a shorter way to think about it, but some people really want to construct the whole thing. So, you know, you do you. By the way, before I get into the next example, this entire sum here, this whole thing, when you finish it off, it comes out to 2.75. Okay, so now what I want to do is I want to basically do the exact same type of example. So we're going to use the function y equals 2x plus 1. So once again, 4 subintervals from the same closed interval. So I just wanted to give you a chance to kind of try this one on your own. So why don't you pause the video here, try to work through this, and then hit play when you're ready. Okay, so if I'm working through this, so I'm going to go ahead and make my little subintervals again. Here we go. And so this time I'm actually going to get the exact area by using trapezoids. I don't know if you noticed that. So we should actually be able to confirm that we found the exact area just by using area formulas, really. Or we could use an integral, whichever floats your boat. All right, so the width, so my delta x is still going to be the same, right? So my delta x is still going to be 0.5, so 2 divided by 4 is 0.5. And then if I want to make my little table of values here, so the exact same thing, so 0, 0.5, that's terrible looking 5, 0.5, 1, 1.5, and 2. Just fill that in. So the nice thing with this example is all of your y values are whole numbers. Oops, and sorry, this is 1, not 0. Okay, so now let's go ahead and do this. So if I want to use the actual trapezoidal rule, so basically then what I can do is I can take 0.5 divided by 2. So starting with this first endpoint, so that I just put in once, and then it's 2 times every other inner endpoint. So let's see, 2 times 2, 2 times 3, 2 times 3, 2 times 4, and then when you get to the endpoints, then you just do those once. So here's the actual sum of kind of what you would do. So if you went through and you actually found the area of each one of these, you should still get to the same thing. So all of this equals 6, okay? So now I should actually be able to confirm this, because if you look at the trapezoids in this case, so it's different from when we were just doing the parabola, right? Because the parabola was a little bit curved. So even though the trapezoids were like a way better estimate, they weren't perfect. But this is just a straight line. So these trapezoids are actually like a perfect estimate in this case. So we can actually confirm this. So I'm going to break this shape now into 2 pieces. So I'm just going to do this now with area formulas, which is going to give me the same thing as what the integral would. So this little rectangle here, this rectangle has an area of 2 times 1, so this would be 2. And then this triangle here, so this triangle, so this will be 1/2, so the base is 2, and then let's see, the height is what, 4? So this is 4. And so of course, then we see that 2 plus 4 equals 6. 6. So they're the same. So we definitely found the right area. So that's kind of it for the trapezoidal rule. So hopefully this was kind of a helpful explanation to you. Will help you remember kind of where the formula comes from. And that's it for this video. If you have any questions or comments, feel free to drop them under the video, and I'll see you guys next time.